So in continuation from the last video, we said that we launched this rocket, and it had this with an initial angle of 46 degrees. So this equals 46 degrees. And we also said that it had some initial velocity, which we averaged out to be, what was it, 44.757 feet per second. Okay, so this graph kind of shows the rocket's flight path, and we know that we can think about this as this is the y direction, this is the x direction. We could also say, and this is the unit vector I direction, and this is the unit vector j direction. So we know that this formula for the position of a unit of the vector at any time is modeled by this equation, x naught plus the initial velocity vector times time plus the acceleration vector times time squared over 2. So we could figure out the position at any time that this rocket was based on this formula. So now it's a lot of filling in the pieces. So let's take it one at a time. So let's start with vector x naught. Well, when we fired the rocket, where was it in relation to its I component and its j component? Well, we started at 0, so we could think that it was going 0 in the I direction, plus how high up was it? It was 0 in the j direction. So that's the first piece. It contributed nothing. So next piece, v naught, our initial velocity. Okay, let's think about this, the angle, for a second. This was 46 degrees. V naught was equal to 44.757. So let's break this down into its x or I, j and I components. So v naught, how much of this initial velocity was contributed into the I direction? Using trigonometry, we can say that v naught, or 44.757, times cosine of the angle times t times the unit vector I. That's how much would contribute in the I direction. Now let's think about this the same way for the j direction. It would be the same thing, 44.757, that hypotenuse or initial velocity, times the sine of the angle times t times that j unit vector. Finally, let's take a look at the last piece, the a unit vector, or a vector. A is what we've defined as the acceleration due to gravity. We know that to be equal to negative 32.2 feet per second squared. So how do we apply that to what we're doing here? Okay, so let's break acceleration down into its I and j components. So acceleration vector how much of acceleration of gravity is contributing to the direction in the I, or x direction? Well, it contributes nothing. It only contributes up and down. So that's 0I plus, what is it doing in the j direction or y direction? Well, it's moving at 32.2 in the j direction. And is it going up or down? Well, gravity always pulls towards the center of the earth. So negative 32.2 in the j direction. And we know that also that's times time squared divided by 2. So if we combine all these pieces together, we know, let's write this again. The position at any given time is equal to x naught plus v naught times time plus acceleration vector times time squared over 2. So the position at any time is equal to our x naught, which was 0 vector, plus v naught is 44.757 times cosine of 46 degrees times the I vector plus 44.757 times sine of 46 degrees times the j unit vector. We're multiplying this entire v naught times time plus, what did we say A was? A is negative 32.2 over 2 times t squared times the j unit vector. So putting these pieces together, simplifying a little more, we get P of t is equal to 44.757 cosine of 46 degrees times I plus 44.757 times sine of 46 degrees times t, and I'm going to factor out that j unit vector, so we can actually change this to a minus 32.2 divided by 2 times t squared, this entire thing multiplied by the j unit vector.